So today we will be talking about uh, a little bit of introduction of machine learning, deep learning, what it means, and then we will see some live examples of building AI models for biomedical images with both a deep learning approach and machine learning approach, and discussing the pros and cons with the different two approaches. And finally, towards the end of the presentation, I would try to cover how you can auto-generate code, C++ code, CUDA code, or even FPGA code if you would like to deploy your algorithm with deep learning, machine learning on biomedical images in an embedded device or even in a cloud-based platform. And then finally, we'll come to the conclusion where we'll discuss a few takeaways and some next steps. So, all right, so a little bit of introduction first. So AI is very, I should say, it's being applied all over in various industries. I think we're living in this mega trend of AI, and medical and healthcare is also not far behind. So we do have a lot of applications in AI as of today. Researchers, scientists in the medical industry have been constantly applying AI for a wide variety of tasks. Here are a few tasks on the screen in which I have companies like Genentech or Idinio. They used machine learning and deep learning technologies for building some algorithms such as tumor detection using CNNs, automated tumor detections, or doing some blood result sample analysis with machine learning. So I think the trend has been growing for the last few years, and medical industry is also caught up to it. So one of the things I would point out, so why Mathworks, and today we'll be talking about Mathworks tools like MATLAB and Simulink. So in the last 2 years, continuously in 2020 as well as in 2021, Mathworks has been recognized as a leader in the Gartner Magic Quadrant for all the data science and machine learning platforms. So when I say a leader, you can see the other names in this square. Along with Mathworks, there's SAS, Databricks, IBM, Domino, and whatnot. So you might have heard about other software tools, but Mathworks is a leader. And today we will see why rightly so it is justified, because Mathworks is not only focused on developing just the AI model, but actually it is focused on the tools help you solve your biomedical problem and lets you develop a medical device or a medical algorithm all the way from end to end. So from all the way from design, requirements, developing the algorithms, and also getting it validated and verified so that it can be certified with the certification authorities. We have the tools to be able to do that. So that being said, what is artificial intelligence? So let's start with a few basic definitions first. So artificial intelligence, I mean, maybe most of the people on the call probably are well aware of this, but just in case if somebody is not, would like to emphasize that AI is the ability of a computer to actually perform tasks which is associated with some intelligent beings like humans. And machine learning and deep learning are the two subsets of our AI, where machine learning involves a practice of learning tasks from data without relying on a predetermined equation or a model. So anything which is not so easy to represent in a mathematical form and we learn from data is what a machine learning constitutes. Deep learning is a subset of machine learning, and oftenly they are used together. Like in today's title, I just called it biomedical for deep learning, but actually it's all AI in my opinion. And it's a type of machine learning algorithm which perform tasks directly from data like images, text, or sound. And what we'll see today is you don't have to do any modifications to the input images to be able to make those algorithms learn. And that's why deep learning is a little bit more powerful, especially in the imaging area, I believe. But another thing I would point out over here is, so machine learning, there's always a feature extraction step. And for a real world scenario, this step can be quintessential for making the algorithm work, but there are some pros and cons to that approach. And the biggest pro being that if you do that manual feature extraction step from your data, then you can actually train some simpler models, which are easier to get verified and validated by a certification authority like an FDA. But with deep learning, the pro is that you can directly train your models on the input data like raw images. But the con with this approach, and it could be, is that deep learning is often criticized by certification authorities like this is a black box network. And with many layers, it's hard to predict, explain the predictions, and then understand the understand the model, and then harder to like verify and validate it to actually put in a medical device. But still, it is very powerful, and people have been doing that. So in this retrospect, the question comes in which direction should we go for our AI? So we have machine learning, deep learning, but I would like to point you out, it depends on where you're at with the data and how much time you're ready to invest in training those models. So I'll give you an example. Let's say there is a lot of pathological image data which you have right now as of today. And so we're here in the data volume, and then you have sufficient time to develop algorithms that you can develop simpler algorithms, but more robust algorithms. Then maybe this machine learning plus a feature extraction approach might be a good one for you. But let's say with a lot of data, you want to develop some quick algorithms in a short amount of time, then you can definitely try deep learning and few approaches which we will discuss today. But having said that, let's say if you don't have enough data and still you would like to see some high fidelity and good performing models in less amount of time, you can add some more advanced feature extraction approach to be able to train much more robust and much more precise classifiers. And this is something which we'll show today. And last but not the least, you can also use models, or what we like to call it as digital twins, to generate some more synthetic data and then use that for training. But again, for different applications, it might be differently. So that being said, I would like to mention FDA's take on AI. So last year, FDA is one of the certification authorities in United States, and they kind of dictate predominantly every single medical device which comes out in the market. And last year, FDA did approve the first cardiac ultrasound software and also came out with some AI guidelines for the certification. And it does believe, and it is encouraging companies to actually use AI and machine learning for the software as a medical device, or SAMD. And it does believe that it can help improve the patient outcomes. So we are at Mathworks are very well aligned with FDA, and anything which we do in AI, machine learning or deep learning, we kind of have the tools. Again, I would emphasize, although it's not covered in today's talk, but we have those capabilities which lets you get those algorithms verified and validated. So, all right, so enough of the introduction part. I guess would like to mention that in this webinar, what I will try to cover right now is I'll show you 2 live examples of using some blood smear image data sets. These are the different parasitology data sets. And I will show you 2 approaches to train different sort of models, deep learning models and then machine learning models with some more advanced and automatic feature extraction capabilities. And we'll kind of compare both the approaches and go over the pros and cons. And towards the end, I would also like to cover this section over here on the bottom right, like how you can deploy those model on edge devices by auto code generation. The material I will send you post this presentation will have a few more additional things associated with it, which like labeling the data set, and then also training like deep learning models from scratch and whatnot. But you'll have those access to all that data and the code files. So in this world, this data set I would like to mention is the data source is a public data source, which is taken from the CDC website in United States. And we have 3 different classes of blood smear images with the babesiosis, plasmodium, and trypanosmosis. So I cannot pronounce it correctly, so you have to pardon me for that. But there are 3 different data sets of this parasitology data. And our task is, as an AI developer, is to build a deep learning or machine learning models to be able to classify these different categories. So with that, I will jump to MATLAB right now, and let's go over this example in a live demo. So let's start with the deep learning approach first. And as we go along, I will talk through subtle points with you. So let me just start. So by the way, this is my MATLAB instance. I have opened a live script, which has like code as well as all of this text data for text for the scripts, like what's going on and some information. So I will be running like one section at a time and talking over about it a little bit in detail. So the first step I would like to point out is the data I have over here is in this folder, which is the data folder. And if you see over here, I have these blood smear images, and the data is already classified or segregated out in the three different categories, which corresponds to the classes to which it belongs. So three different like classes over here. If I see in, it is that this again, I cannot pronounce this word, but Plasmodium babesiosis and the third category. And if we see over here, we've got these JPEG images for all these different categories. So let's try to take a look at one of these images just outside. If I try to open it, actually, you know what? I don't have the photo editor on this machine. That's okay. Let's go back to the script right now, and let's actually try loading these images directly in the script. So the first thing I'll do is I would actually, for the training piece, I need to bring all that data in MATLAB. And I do not have to load all the data. So right now I have a few data sets. And in this case, if I see the data set, let me just show you this part. So I have around uh, uh, around 17 images for the first class, and then I have like 87 images for the second class, and then another 17 images for the third class. So the data is a little bit of unbalanced, but the idea behind over here is like I don't have to load each and every file in my memory to start training the deep learning models. What I can do is I can create what we call as an image data store, and we just need to point it where my images exist and give the properties such as the label of those images is my folder names, and we want to include subfolders, and then we also want to say that the file extension are JPEGs images. And what it does is it creates this image data store object with all the paths to the to my images where they are residing, and corresponding to all these file paths, we have the associated labels which would be used for training purposes. So here is all the labels, all the three classes. Now, that being said, since now we have imported the data and we know that how the data looks like, we can probably go about and see some of those data sets to visualize some of the data sets. So in this lines of code from 11 to 15, I just randomly like pick a few images from that data set, and I read it, and then I just plot it. So this is how the different images which I have look like. So if you take a close look at these images, you will see that each image, even of the same classes, is different. And this is actually a complex task in deep learning to be able to train a high fidelity model. There are two challenges in this kind of image. The number one challenge is like we do not have enough data. So there's only like 119 images, which is very, very less if we talk in terms of deep learning. But then the second and the bigger challenge is that if I see the babyosis classes, all images look very different. And if I look the Plasmodium, even in this class, the images look different. And this is the same for the third class. But however, our task for the deep learning is to be able to identify the commonality of features in these set of images, and train a model which actually differentiates all of these images from the features which is different from this class and the features which is different from this class. So the task is complex. Again, the two reasons for it. First, we do not have enough data. And the second is that the data sets are pretty diverse. And it is, like, let's say I'll give you a simple example. Let's say if I had to train a network which is differentiating cats from dogs, I think that is a lot more easier problem to solve as of today with deep learning, because cats look very different than dogs. But then having said that, uh, uh, so the deep learning is very easy to implement in those kind of problems. But here, they're all cells, they all look alike. And there's the subtle differences in these classes which needs to be captured by the deep learning network. So that's our challenge over here. So now how do we go about it? So there are two approaches with the deep learning. So the first approach is like you can always start from building a model from scratch, where you can define all the deep learning layers, connect them together, and start training on your images. For those of you guys who might be new to the deep learning aspect, I would like to point out that there are some more material which we have, which goes over in detail about deep learning. But for today's talk, I won't be going over too much detail, just a little bit of outline. Oops, I'll swap this. that the deep learning network under the hood uses a neural network architecture. And what it does is you've got this input layer which takes in the images, and then it's followed by a series of different layers like convolution layer, ReLU layer, uh, uh, max pooling layer, and then there's a whole laundry list of layers which actually transforms the images from one stage to another stage to another stage to another, such that the output layer is giving me the prediction, or it gives me the probability of the different classes the network is trained on. So let's go take a look at one of this network, which is called Alexnet. And Alexnet is one of the public networks. And if you take a look at it in, if I just do, let's say, a Google search even on Alexnet, you will find that this is a public network. You have a wiki article on it. And this is one of the deep learning networks, which is taken as a standard. It was developed in 2012 for classifying 1,000 different classes of objects, real world objects, as a part of the ImageNet competition. So I'll paste this link in the chat for your reference right now. Feel free to read through it. And again, this is me kind of like glossing over the deep learning concepts, but if you would like to learn a little bit more about deep learning, then we do have other sessions tailored towards that, and we would be more than happy to discuss that with you. So please let us know. But in this one, let's load in this Alexnet, and let's try to take a look at what Alexnet does. So I just call this function. MATLAB directly supports a wide variety of pre-trained models, and one of them is Alexnet. And if you'd like to take a look at what other models MATLAB supports, then you can always do a Google search, MATLAB deep learning pre-trained network, and it will bring you to this list of networks. And there's a whole library of networks, and then we talk about which network has a better performance and which network to use when. Like Alexnet sits over here, the accuracy is not too great, but the speed of prediction is very, very high for Alexnet, and so forth. You can read through this entire page to understand what are the different networks. So I'll just paste this link also on the chat for everybody's reference. But I think the important factor to consider here is the accuracy, and then at the same time the size. If the size of the network is small, it can fit in those smaller embedded targets. But if the size of the network is large, like a VGG16 or VGG19, then you can see that it's got like 500 of MB space it needs to be put on the embedded target, which can become challenging at times. So it's a pretty good way to take a look at it. But for now, let's focus on our Alexnet. So I have already loaded the Alexnet in my workspace. And let me just run this command, analyze network of Alexnet. So let's take a look at what Alexnet does. So Alexnet, like I said, is a network which has different layers. It takes in an image of size 227 by 227 by 3. So the input has to be of size, the input image has to be of this size. And like any other deep learning network, it's got one layer after the other, convolution layers, max pooling layers, and all the sorts of different layers which are possible. And last layer, if you take a look at this closely, is a classification output layer. And in this one, what it's doing, it's a size of 1 by 1,000. So it takes in the image and converts it into a vector after the series of transformation of 1,000 different classes this network is trained on. And for each of those 1,000 classes, what is the predicted score? So let me show you a quick demo on this one. And we'll use this network for our particular problem. So let's say if I load in an image of some random object, let's say, let's forget the biomedical image right now. But let's say that I just load in a image of a peppers, and let's view this image. So this is my image. So this is an image of some bell peppers, some other pieces to it. And what I will do is I'll pass this image through the Alexnet. But remember, I said Alexnet takes in the image of size 227 by 227 by 3. So it is important. Right now, my image is of different size, which is 384 by 512 by 3. So it's important for me to resize it. So I'll just do that over here. I am resize of IM, and I'll just call it like, hey, change the first and the second dimensions to 227 by 227. The third dimension is by 3. And then I can call net.classify and throw in this image IMR and get my output. So once that image passes through that network, and layer after the layer after the layer, it does do a classification. It's just taking a while, not sure why, but it will give us a classification. And what it does is, there we go, it classifies that image as a bell pepper. Now note that there are 1,000 different classes this network is trained on. And if you'd like to take a look at the classes, you can always open this layers and read those different classes in this classification output layer. So if you see this classes, then you'll see that this network is trained on some real world objects like robin, bulbul, different birds. If you scroll down, there's slug, sea slug, chitin, there's papillon, Afghan hound, some different dogs, uh, and all sorts of 1,000 different real world objects. So that's what Alexnet is right now. But now we have this whole different deep learning networks already available for us. And what we can do as of today is use one approach, which is called transfer learning approach. And we don't have to construct all this deep learning network from scratch. But what we'll do is we'll modify that network, tweak it a little bit, and retrain that network on our data of this biomedical images and see what's the output we get. So in the next section, that's what I'm going to do. So just take a quick look. But before I go to that training part, I just want to make sure. So this was a little quick spiel on deep learning, but are there any questions at this point on deep learning, or any more questions on Alexnet or anything which I've talked about, layers or the different pre-trained networks? So please post them on the chat. I'll be happy to take them. All right, silence is no questions right now, but guys, please feel free to keep posting the questions on the chat. I would be taking them as we go along. So right, I think I'm getting some internet issues at my end. Apologies for that. The network is not responding properly, but let's continue on regardless. So I'll go back to the slides right now. So what we'll do right now is I would like to talk about one additional thing before I get back to MATLAB, is that so as of today, I did show you the pre-trained network like Alexnet, but for that matter, you can bring in any network like from TensorFlow, Caffe, PyTorch, MXNet, so any deep learning network you might be working at, you can bring it in MATLAB and start retraining it for your transfer learning approach. And in the transfer learning approach, what we do is we just take those networks, which is already pre-trained. Let's say you find a good network like a UNet, for instance, on internet, and you can import it through, bring it in MATLAB through the ONX exchange. And now you just have to fine tune that network and retrain it on the new images. And that's what we're going to see right now, and to classify this new images. So let's take a look again and see if hopefully my network has restored, but getting some issues. Let me just quickly reopen MATLAB again. Sorry about that. Not sure what's this is what's causing this issue right now, but let's go and retry it one more time. And also, guys, in the meantime, if there are any questions, please keep them coming. More than happy to answer it as we go along. Let's get back to this. Right, I'll just quickly run the few sections like we had already run before. in the beginning and then go to the training part directly. So I have already prepared the images. I have a Alexnet, which I'll be working off from. And what I have right now is I've created this image data store and whatnot uh, for doing my image classification. And one more thing I would do in this exercise is that since the data set is unbalanced, so for a comparison perspective, what I'll do is I will actually take in all these images and do a quick reorganization. So what I'll do is, let's just do this. I'll run this over here, and I'll make this data set to a little bit more balanced data set. And I can call these functions, which are integral part of the image data store, which allows you to split your data in training and test data set. And what I've done is right now I split each of these classes in a balanced data set. And I'm doing like, I'll reduce the data set and then train it using a certain number of data sets for training, and then have some data sets saved aside for my testing and validation purposes. So one more thing I would like to point out is another feature of MATLAB before even going to the training part is that you can, because the data set right now I'm using is a very small number, you can actually automatically apply data augmentation techniques to those images to create more new data sets from the existing data sets. So we have defined this augmenter over here, which is connected to the image data store and which does tasks like random reflections around the x-axis, translation around the x-axis, y-axis, rotation of the images and whatnot, and creates more higher fidelity of your features, which the deep learning network can learn from. So I have this image augmenter over here. Let me just define it. So this augmented image data store, what it does is it will resize all my images to suit the requirements of Alexnet, and then at the same time apply all these image processing functions on the data sets. So now that being said, the third step, which is like the actual training part, is pretty easy. And what I'll do is I will open this app, what is called a Deep Network Designer app, which allows us to kind of very easily just take all the data which we have kind of transformed and build it off of deep learning network and to train the model of it. So again, we'll be using the Alexnet, but you'll see right now how easy it is to do it in MATLAB and test and prototype so many different types of network in just one platform. So if you go to this apps, you can find this deep network designer, which I've opened over here in the category of deep learning and machine learning. And there are other apps as well, because I have all the toolboxes. That's why I have so many apps right now. But if you see this app over here, so I can either start with a blank network or I can choose from a pre-trained model. And in this case, since I'm using Alexnet, I'll just scroll down and open Alexnet for now. And this GUI-based app allows us to kind of interactively construct, remove layers, add layers, and change the network parameters, and then interactively, just on the app itself, perform the training and analysis of the network. So let me show you what the transfer learning approach, I'm going to do is, I still have all those layers. Like the first layer is, so this is my canvas. On the left side, I have all those layers library. I can drag and drop and put layers for deep learning. We'll see that it's got all the different layers. But this is my AlexNet network. And because it was trained on the 1,000 different categories, which is evident from the classification layer output size, what I can do is I can delete this classification layer and fully connected layer and add a different layer. So this is what transfer learning is about. Change a few layers and adapt your problem to the new data set. So over here, I can connect this layer to this one, and then also add a new classification layer, just like that. And in my fully connected layer, just define that, hey, my output size now, it's not 1,000, but it is just 3. So this will take care of the new images, which is coming in for this biomedical images. And you can again go ahead and analyze this network just to make sure that we have not made any errors, and it's got 0 errors, 0 warnings, and it's the same Alexnet over here, but you see now the output size is transformed to 1/3, which is going to be for our 3 different classes. Once I've designed this network, I can go to and select the data. In this case, I can import the data from my workspace. And this time I already have this augmented image data stored. So I'll just use that. And right now I do not have any validation data. So I'll just select none and go ahead and import that. So here are the different images, and you can see that the augmentation has actually applied to the images. It's rotated, translated all the different images of different classes. So we are set on that. Then we can move to the next step, which is the training. Now, training is the step where actually the deep learning network would learn all those parameters from the data, and you can define different training options using this training tab, which solver to choose from, what is your learning rate, and in this case, I'll just reduce the learning rate by little volume right now, and all the different parameters like the maximum epochs or the mini batch size and whatnot. And one important parameter over here is like which platform you would like to use for training. So as of today, if you take a look at this list, we do support GPUs as well as multiple GPUs to advance your training. But then also, if you want to train on the cloud like AWS, Azure, you can do that by selecting the parallel option. And if you're connected to a cluster, then it would automatically scale the training on your cloud environment. So right now I'll select the auto because I have already a GPU on this machine I'm using, and I would let this network train on the GPU connected to it. So let's go ahead and hit train, and we'll see that the network would begin training right now. It on the GPU, because there are not many images, the training process is pretty quick. It does train, and you'll see like the network will start to converge within a matter of few seconds. So you can see that my training environment right now is single GPU, and let's let the network train for a while, and it would start to converge pretty soon. So now the training has started. Not many images. Usually the deep learning does take a while for training, but in this case, I think, and pardon me, my internet speed is also, I think, is limiting, and that's why some uh, some pieces of the demo is like taking a while to run. But you'll see that my network is learning right now. Accuracy is improving. The loss function is it's decreasing, and within a matter of few seconds, the network usually gets fully trained on a CNN. So once you're done training, like at this point, it has reached its final iteration, we can go ahead and export the network. But everything we did on the app, we can also generate a code so that, let's say we want to reuse our framework for retraining different networks. I just did AlexNet, but you would like to use other networks, then you can very easily do that from here. So right now, I'll just export this network for now, but let's go ahead and go back to MATLAB. And if I, actually, let me go back to this. So I would like to show you the code which it generates. So everything we do on the app, it creates like a good, nice script for us, which can be reused for future trainings and whatnot. So this is all the script which it auto-generated, and you can see that it created all these layers, and the layer size is 1/3. And then I also call this train network over here, which is pretty much automatically done. So on the script, I do have this all laid out in a script, but let's go ahead and test my trained neural network on a test data set. So the last time when I trained it, so what I'll say is this network which I exported out is my train network. I'll just rename it as my net. So this is the one I just exported out right now. And let's go ahead and call the classify function on this MyNet on the test data set. And what we see is that the network accuracy is kind of okay, not great. The network accuracy I got was 80%. And you'll see that a few of the classes, the test images set, were not correctly classified. So CNN, long story short, is a good way. So like going back to that slide, you would have seen that in a few lines of code, if I do not have enough data, or if I have enough data, and this is the approach I took, let me just go back to that slide one more time. let's see if I can find it. Yep. So this is the approach which we just did. So in our case, although the data volume was low, but still it was very quickly to train a CNN by transfer learning approach. And within a matter of few lines of code, I can, and using the apps and whatnot, I can quickly train the network. So pretty easy to use, but I would like to open the floor to questions before I go into the more practical approach with using this part over here, where we can train any classifier and get a much higher accuracy. And the speed of the network would also be pretty phenomenal. So any question at this point, would just like to take it right now. All right, I don't see any questions, but guys, please keep the questions coming. So I will go to the next part of the talk, which is a more powerful approach, and which is, I would say, more practical for biomedical images. And that's what I see in the industry. People are moving towards more and more, and becomes all the more practical when it comes to verifying and validating the model. And I'll show you how and why. So in this example, again, it's the same data set, the same image set, but what I'll do is I'll again load this image using the image data store, but this time I'll train a machine learning model, a simple machine learning model, and show you how easy it is to go about by this image classification problem if we use some additional feature extraction technique. And the CNN has its own challenges, that it's pretty deep, 25 layers, and the accuracy is not good enough. But with this technique, even with the less data set, less amount of data set, we still can extract those subtle features from the images and train a pretty high accuracy model, which would be pretty robust. So right now, again, I do the same thing. I split the data in the training data set and test data set. It is an unbalanced data set, and you will see that in this example, even with unbalanced data set, I get a fairly high accuracy. So what I'm going to do in this example is do a little bit of image processing before doing the deep learning and or the machine learning. And what I will do is I will just call this function wavelet scattering, and I will have this wavelet scattering network extract features from the images. So for those of you who do not know wavelet scattering, let me just pull up one more slide just to talk about it. So the wavelet scattering network is actually, remember I said that it's very easy to verify and validate. So it is analogous to a deep learning network like a CNN, what we saw, because CNN had all these layers like convolution layer, rectified linear unit layers, max pooling layers, and whatnot. So wavelet scattering network is similar in that sense that it also has a convolution layers, but this time we're extracting features by convolving it with different wavelets. Then for the non-linearity operation, we have some modulus operations, like where we're uh, applying a modulus to the data. And then we're also doing some averaging. And layer after layer, we kind of split the image into those, throw it on those filter banks, and we get some outputs, which we call the subtle features, which can be used for classification. So when I talk about the layers, over here, let's say we have an image coming in, which we have this, like, this is the image matrix, so it's can be of any size. And then for each layer, we would get some scaleogram coefficients as well as scattering coefficients after doing those transformations with applying a wavelet filter and a scaling filter from a layer after the layer after the layer. So this is a convolution with a scaling filter, and this is modulus operation with a wavelet filter bank. And then we get all these feature matrix, which we can directly use for training. Now, the long story short, the takeaway is, for doing all of this, we don't have to write any lot of code. We already have a function in MATLAB, which is called wavelet scattering. And apparently it's proven over and over again. You can find a lot of literature that it actually not only extracts the subtle features from the images, like in this case, our images of size 300 by 300, this one line of code will split the image into much smaller subsets. And in this case, for each scattering transform we do on the image, it gets converted into a size of 300 by 300 by 3 for RGB image gets converted to a size of 27 by 38 by 38. So which is more than 70% of the reduction in size. And as a matter of fact, for this 27 different scattering paths which it create, we can even average all my coefficients and use it as one training data sets. And that's what I would do for training this machine learning model. So I have this function over here, which actually calls the feature matrix on the wavelet scattering network. So this will give me a matrix of size 27 by 38 by 38 by 3. And I would just call this mean for the 38 by 38 by 3 and call my feature. So long story short, over here from all my training images and all my test images, what I'm doing over here is calling that wavelet scattering network from each image and converting it into a train and a test data set, which can be used to train our deep learning and a machine learning algorithm. And if you see over here, the size, the dimensionality reductions, in this case, I'm taking all the images. So what I have over here for the train images, I converted those train images. So I had, let's take a look at this. Train features. So I had 116 training images. And for those 116 training images, for each image, I have 27 different feature size. So I can use this, I've kind of deconstructed that image to a vector of size 27, which represents the subtle high fidelity features, which differentiates all the three different classes from each other, and then also captures the similarity in one class. So huge, huge, huge value add. And I would again emphasize that this process, wavelet scattering in 2 lines of code, it can be 100% verified and validated. It is not a black box. The wavelet coefficients and the filter banks are known. And it's as simple to verify and validate those feature extraction method is as simple as doing any other low pass or a high pass filter for that matter. So we have constructed this training features, test features matrix, and for all these 116 features, we have this labels, which is in this vector, which is called train labels, which is over here. Train labels, let's take a look at this. So 116 by 1. And now we'll train a machine learning algorithm. And again, to train our algorithm, we'll go back to our graphical interface and go back to this section and open this new app, which is called a classification learner app. So in machine learning, like one of the questions does come up, like which algorithm to train from. Same as for deep learning, like you can use all the different pre-trained networks to train from, or you can try with one of those. And in this one, with this app, what it allows you to do is actually train all the classifiers and see what classifiers give you the best results to go on from there. So let's select our data first, and then we'll see this live as well. So we have this train features matrix, which is of size 116 by 27. And for the response or the output, what I'll say is that, hey, my output is this train labels, which is 116 by 1 categorical. So 116 images, 27 we have predictors. We have 27 predictors for each image. And this is the feature set I will use to train my machine learning model. So now going back to that question of which algorithm to train from. So this app will allow you to choose from all the algorithms like SVMs, KNNs, different trees. You can select, pick and choose some of the algorithms, but you can also select all the algorithms if you're not sure which algorithm would give you a better result. And in the interest of time, what I'll do is I'll just select all quick to train in this case, and just go ahead and train a few algorithms and see which one is giving me what degree of accuracy. And while I'm doing that, guys, I have opened another poll for us because we're kind of at the last 15 minutes. So if you can take, actually, you know what? Let me just cancel it and reopen it. Sorry about that. Actually, my apologies. Let's open the poll a few minutes later. I, I I think I should just wait for a. I did not realize the time right now, but let's get back to over here. So my algorithm is trained, and which I'll see is like the KNN is giving me the highest accuracy, and you can see that the different algorithms are giving me accuracies. And if you see closely over here, the highest algorithm, like with the fine KNN in this case, already got a 92% accuracy on an unbalanced data set, which is huge. So going back to the CNN example, like we got it only of 80%, but in this case, we're already at 90%. And right now, I haven't even tested out with all the algorithms. And as it turns out, when I was experimenting with the different ones and the SVM algorithm, the support vector machine, this cubic SVM apparently gives me a much better result, and we can just try it again over here. Just retrain this cubic SVM as well. Uh, uh, and you can you'll have to change a few parameters, like some hyperparameters for the SVM, like this box constraint level and this kernel scale and whatnot. But you can see that very quickly you can test out different machine learning algorithms and see the results and whatnot. And once you're, again, just like the deep learning designer app, once you're done with training, you can generate a entire script if you'd like. So this is my function which does all the deep learning training, or you can also export your model in your workspace. So in this case, let's go back to the script right now. In this case, I do train this template SVM, and this is the code to uh, uh, train this template SVM with a polynomial of order 3. So it's a cubic SVM in this case, and this is the box constraints size and kernel scale I used. So once I do that training and I test my accuracy on the test data set, again unbalanced, and see what I got. I got 100% accuracy. So with deep learning, despite that huge network, it was only 80%. But in this case, with the unbalanced data set, I got 100% accuracy. And I would like to point out the only reason why I'm getting that 100% accuracy is because we did a rich feature extraction step. And now my SVM is a lot more easier to verify and validate with certification authorities because it's a simpler network. But then I have a pretty robust model which can be used for other images, and I have a very good model which with a good accuracy result. And even if you go ahead and test more images, like get the precision, recall, and whatnot, you'll also see that with good feature extraction methods, you can train these models which give you a much more higher fidelity than what a simple transfer learning approach would give you any given day. So we'll take a pause again. Any questions at this point? Any more questions? So we do have a question. I will share all this code with you, and then I will also share all these slides with you after the session. So definitely, there would be other code as well, like improving my accuracy of the deep learning model with different techniques like Bayesian optimization, which we won't be going over today. But I do want to talk about a last piece in the next 5 minutes, which is about the deployment process, and you'll see that code as well. So, but any more questions right now? All right, no questions. So let me go to the final piece of the presentation, and then I'll open the floor again to some more Q&As. So once we have developed this AI models, one of the important things for our medical manufacturing and instrument manufacturing people are to deploy the system. And as of today, you can actually take these algorithms directly from MATLAB and deploy it as an enterprise system on the cloud, like AWS, Azure, and whatnot, but then also generate some code which can go into the CPU, GPUs, or FPGA, different embedded targets. So one thing which I will show you right now is that I would take this. We have the tool which is called coders, like HDL coder, GPU coder, CPU MATLAB coder, which generates the CUDA HDL codes for the different platforms. And what we have over here in this particular example is now I have all this like deep learning as well as machine learning models. And if you open this exercise over here, like I've got these files, and this is the same folder structure you will receive. But in the code generation piece, what I've done is I've actually packaged that classifier, the final network which was giving me the accuracy. I put it as a function which will reside on my target. So I call this classify parasitology GPU. And what I have is, like in this case, I'm giving an example where I'm targeting for an embedded GPU, like an NVIDIA Jetson board or an NVIDIA Nano board. So I take in an input image, like if it was reading from, let's say, a microscope, and I load in this network, which is a deep learning Alexnet network in this case. and I resize this input image to the size of Alexnet, which we had done before. I am resize, and then call this classify function on that network with the resized image and get my probability. So only 3 or 4 lines of code is all I need. And what I can do is, now once I have this function in MATLAB, I can go ahead and, let's try to test that function out by reading one such image and calling that function. So if I call that function just like that in MATLAB, so we're not doing anything on GPU, but it's just giving me taking the image and giving me the output class, like in this case, Plasmodium. And what I can do, again, going back with the apps, I have this nice app which is called a GPU coder. I can open this app and generate embedded CUDA code from this entire function, classify parasitology GPU function, so that which can reside on embedded target like NVIDIA Jetson, NVIDIA Nano, or it can also, like, you can take it in it generates a CUDA code in this case, so you can even take it outside this environment and have it deployed elsewhere. So I can just, the way to generate the code is again through this app. I can specify the function name. The function name is classify parasitology GPU, and all right. So it is kind of, it gives you this walk over of what to expect. And then the first step is, okay, what is my size of my image? So I can just input, like, because I have one of such image in the workspace, I can just enter that, and it automatically figures out the image is uint 8 of size 300 by 300 by 3. Go to the next step. And I'll skip this for checking issues in the interest of time, but at this point you can specify what are your objectives. So are you going to generate just a source code, or you want to generate a standalone executable or a binary library for dynamic linking? Or you can also just generate a MEX, which generates a code, but then it compiles it to run on MATLAB itself to test out the speed. And in this case, that's what I'm going to do. But over here, you can also specify your different hardwares in case you want to generate like a executable on a hardware like Jetson or an NVIDIA drive. You can definitely choose that. So I'll go ahead and generate a MEX. And if you click generate, what it would do is it would translate all of the code inside it. So any image processing, any wavelet scattering, anything you're doing inside this function, it will automatically convert it into a deployable CUDA code. It does take a while to generate, but you'll see that it would start creating all these files, .cu files and .h files over here in this folder, and it will compile it in a MEX format so that you can run it on a GPU inside MATLAB as well. So we'll take a look at the code real quick. Let's see if it opens in the next 1 minute. It does take a while, like I said. So I don't think my environment is fully set up to run it, but you see these are all for the deep learning layers. We do support like the TensorRT library, as well as we support the CUDNN library. So for all these layers, it has generated all this code, and all the CU files and .h files, which gets compiled, but I have not set it up correctly right now. So that's why, I think I'll have to set up the NVCC, which, let me just do it right now. Yeah, I think never mind. We can skip this step for in the interest of time. The NVCC probably sometimes gives, you have to have the compilers ready. But the last time when I ran it like a function which is mixed on a GPU versus CPU, you'll see that you'll get a significant speed up. So in this case, like when I was compiled it and I ran it on a GPU on my machine, I did get a speed up of 2.4 times, and it can easily be kind of put in a reference target and whatnot. So that's like auto code generation is the biggest takeaway. And going back to the slides right now towards the conclusion, I would like to point out, so first of all, I've opened a poll. So if you can take a few minutes to fill out that poll right now, I would really appreciate it. I would also point out that we have, the content I covered today is just like an high level overview of some of the functionalities like training machine learning, deep learning, and then auto generating the CUDA code. but Mathworks and TechSource are your AI partners. And if you have an AI task like biomedical images or biomedical signals, feel free to reach out to us. We'll be more than happy to assist you, guide you, and help you develop the end goal.